So I'm Christian Stolman. I'm a sophomore here at UWL, and my majors are math and physics, just as kind of a quick background of who I am. But the outline of my presentation is going to go into the introduction of the competition, and then I'm going to explain the idea of object detection really briefly, and then go through the structure of what NASCAR CNN was, which was a heavily used model of the competition that I competed in, and then the approach and process that I used, as well as the table of results, and then the winner solutions and future work. So for my introduction, Kaggle, for those of you that don't know, is for data scientists to go through and compete against one another. And the great thing about it is typically they're given a monetary prize. So that's a lot of the drive with these competitions. And it's also funded by Google. With this, I specifically work with the RSNA pneumonia detection challenge, and the big question that's being asked is, can you build an algorithm that automatically detects potential pneumonia cases in patients? And so the goal, of course, is going to be drawing bounding boxes, which are these boxes that indicate where the pneumonia would be located. And I'll be using the words lung opacities often, and that just indicates in a grayscale image any kind of gray area that would show up as potentially being an indicator for pneumonia. So in this image right here, you can see that the blue box is going to be the ground truth. That means the actual place where 10 or 20 actual doctors and nurses went through and studied these specific images and said this is where the pneumonia is located. And this is one of my models predicting in the red where the pneumonia would be located. And the way that the grading went about was intersection over union. So they'd take the area of how accurate, they would determine how accurate you were based on the area of the ground truth and your prediction, divided by the union of the two images together. And so as you can see in these specific areas, on the left side, the lung opacity and prediction box area is actually very well fit, whereas the one on the right side is not at all. And so that's what we're trying to aim for, so that your maximum, or that the maximum score you could receive is 1, which would be 100%, which means every single prediction you have is over that ground truth. And so the competition timeline started from August 27th to October 31st altogether. The start of the second stage was October 27th. And then I personally joined on September 26th and then only submitted my first model on October 10th, so I kind of got a late start on it. For stage 1, I landed 319, and for stage 2, I landed in 39. And I'll give the more accurate percentages later to kind of keep you guys intrigued so I don't bore you up too much. For object detection, there's 3 main ideas that are really associated with this that I ended up working with. The first one was classification. So it's asking the question, is the object, or in this case specifically, are the balloons in the image? And so of course the answer is just going to be yes or no. And then with localization, you're going to put boxes over the specific areas of where those balloons are located. And those are going to be the output of the bounding boxes. And then segmentation, which is what is the shape of the balloon that I'm looking for? And so the output is going to be masks or regions, and I'll refer to those as masks or regions often throughout the rest of this. And so with regional object detection, it uses all 3 of these ideas and kind of concatenates it into one final idea, which is regional object detection, and uses the sliding window method. So as you saw in Cassie's presentation, where she went through and slid that filter over those various areas of the pixels, that is the sliding window concept. Whereas with a faster object detection, you have a single shot. So I'll explain in a little bit, but YOLO uses this idea, which stands for you only look once. And it goes ahead and places all of those filters over every single spot, and then indicates how close it could have that object into the image. And so with object detecting CNNs, it goes through with the CNN filter, and then it asks, are the balloons in the image? And so of course it's only a yes or no, and predicts where the balloons are based on the significance of the pixels. And then if not, of course the model just ends there. And then of course you're going to modify your model to become more accurate, so the predictions are going to be more accurate. And so with regional, it adds a little bit of an in-between step where it has this idea of region of interest, or ROI. And in here, it predicts where the mask would be, and so it tries to fit that mask over where those long opacities, more specific to what I worked on, would be. And with object detection, so there's two main routes that you can go down. The first one is regional, where you're going to have a bunch of different ideas from RCNN to faster RCNN, and then of course mask. And then with single shot, where it places all of those possibilities over on the image all at once, and that would be the idea of YOLO, or SSD. The advantage to using single shot is that it's very fast. The unfortunate aspect of it, though, is it's not as efficient. Whereas with regional convolutional neural networks, it's a lot more accurate. And so after doing extensive research to see what other competitors were doing, I noticed that mask RCNN was something that stood out. A lot of competitors were working with this, so that's something that I, of course, wanted to try. And so with mask RCNN, this is kind of the general structure that it took. And I'll kind of go into a quick in-depth explanation of it, but basically what you do is you have two aspects of a model. You have training / validation as well as testing. And so this is kind of the general structure of training and validation. You take labeled data and you know what the answer is. So you're feeding that into your model and you want to be able to predict as accurate as you can where those long opacities are going to be. And so there's this second part, which is called validation, where you still have predictions on, or where you still have labeled data left over. And so you split up your original data set and you make predictions onto the labeled data to just see how accurate your model is doing. And then, of course, you ask the question, how accurate is it working? And then you update that accordingly. So with that, the classification, localization, and segmentation are kind of like displayed above with the specific ideas of CNNs. But then there's also the testing stage, which makes the predictions on the unlabeled data, which of course is how you get the ranking in Kaggle. So of course you want the highest accuracy possible, and the highest score you could get is 1. And so with this, the idea and structure of mask RCNN changes just a little bit. So it uses that segmentation where it refined those masks to get it as accurate to the shape of a long opacity as possible, and it's searching for that throughout your image. And then segmentation idea is used there, incorporated to say, well, in this case, where's the shape of the soccer players? Then it goes through and classifies. It says, okay, so ultimately, are there soccer players there? And then finally, the last stage would be localization. So it's putting a box over the area that it's predicting for the soccer players to be. And so with the competition approach itself, I ultimately identified two main ideas that you could go with. You could either go wide or deep. With wide, you'd be testing many different models, many different techniques, but with deep, you take a single model and you do all details, that hyperparameter or fine-tuning. And so I decided I wanted to work with wide because this is a generally unexplored area, or it's a very relatively new area to the idea of computer science and neural networks. And so I explored 3 primary ones, which was ChexNet, which stands for Chest X-ray Network, and then YOLO V3 and mask RCNN. And then I tested many, many different techniques. And so this is kind of, I don't want to lose you guys in this too much, but there's a bunch of different techniques you can take. But with that specifically, the ones in green are the ones I decided I wanted to work with because it seemed the most relevant. The ones in yellow are the ones that I'm currently still researching or working with. And the ones in red are things that I kind of ruled out as not being as useful for a network to work with. And so my process would be, I would choose one of those specific models and then choose the parameters and add or remove techniques based on what I think was most accurate. And then I would go through training and validation, and then of course analyze the training and validation loss. And so analyzing the training and validation loss is arguably one of the most important parts of building a model. And so as you can see here, loss is actually equivalent to error. So every time that I refer to error, or every time that I refer to loss for the rest of this presentation, just think of it as a sort of error in how bad your model is doing. So of course you want to minimize that, but you want it to be a smooth descent. And you can see the one on the right is it's bouncing around, it's not accurate, whereas the one on the left is significantly more smooth compared to it. And you also want to minimize the gap between your train and validation losses. So as you can see, you're never going to have a perfect model. You're always going to end up having some kind of gap, but it's trying to minimize that gap as much as possible. And so with the one on the left, it's got much smaller gaps between training and validation, whereas with the one on the right, you have much larger gaps when it was bouncing around. And so of course you want to fit closer to the model on the left. And so after you've gone through and you've tested many different models, updating various different models, you go through and you analyze every single model and every single training and validation loss over all of the set, and then you submit the most promising model based on the lowest loss, which is of course the lowest error. And so with the loss function, don't get lost in the math. The idea with MaskR CNN is that it uses the loss of classification, bounding box, and mask. So those three ideas added all together to give you one final loss, and it determines how accurate your model is working. And this is the most accepted and precise equation for MaskR CNN. YOLO v3 uses a different kind of loss function, which is with no object, the loss of not having an object in the image versus having an object in the image. And that's the mathematical concepts behind that. But this one is also a very widely and precise equation, but it could be refined a little bit more. There's arguably been people saying that YOLO v3 is not nearly as accurate as MaskR CNN, so this is something to still be explored. And then ChexNet. So because ChexNet is such a new idea for models in neural networks, there's no generally accepted loss function. And so this one I had to kind of derive on my own. But I started out with using an idea of what someone else had posted on Kaggle, and then I kind of worked with it a little bit. And what I found out was this loss function absolutely sucks. Do not use that ever if you're ever going to do neural networks. But it was a good place to start for exploring the idea of what I can work with in a loss function. And so with my table of results, there's the three ideas, like I said again, for the models, which was MaskR, CNN, ChexNet, and YOLO. But then I used four primary techniques, which was optimization, which tries to smooth out that curve for the loss of both training and validation, but also the learning rates, which again, also kind of smooths out that curve for the loss, but it also decreases that gap. And then training and validation set split because that's on the label data, so you have to be able to split that accordingly to see how accurate your model is working. And then the various configurations, so just fine little details that are within the models. And I used two primary clients, Kaggle and Google Colab, and each of them had their own advantages as well as disadvantages. But these were just some of the ones I was able to come up with. But overall, Kaggle was much more user-friendly, whereas Google Colab was not. It was very intricate, but I was able to pick up on it after working with it for quite a while. And so for this table, I'll be going through, and the Ks indicate where I worked with a Kaggle client, and GC indicates the Google Colab. And with this, you have the various optimization algorithms that I worked with, as well as the learning rates. And so ultimately, I was able to pull out this chart, and each percentage indicates the accuracy of IOU. And everything that's bolded, as well as italicized, is the best in that specific row. And overall, you can kind of see that the highest percentage that I was able to pull out so far was 15.27%. And so going through training and validation, as well as configurations, I was able to pull out this idea. And so the percentages in this table also indicate accuracy, but for the configurations, these are more specific and fine-tuned little details. So for my final results, the total number of models that I ran ended up being 54, which is a huge amount of time that I invested into this, considering that each of the models themselves took about 7 to 12 hours. But I wasn't sitting around just waiting for my model to be finished training and testing. I was researching how I could further my model and what's the next step that I could take with this. And so the total number of models that I submitted was 37 because you could only submit 5 per day, so I had to kind of pick and choose which of the models I was going to submit. And then the total models for final scoring that I was able to submit for stage 1 versus stage 2 was only 2, of course. And so the big question is, what was the best model? And what I was able to pull out was MaskR CNN with COCO transfer learning, as Cassie was talking about in her talk, with using the Kaggle client. And then it had a 15.27% accuracy. And although that might not seem that it's very accurate, it was actually a very significant difference. because everyone that was below me, the next closest person, I would say, well, actually was pretty close, but within a percentage of that, it had a variance of 16 to 12%, and it was incredible. But the biggest part that I was able to pull out from here was that it had a 93.2% accuracy for classification. So 93% of the time, it was able to correctly and accurately tell whether the patient had pneumonia or not, which is arguably just as important as being to identify where, if not more. And so for stage 1 versus stage 2, in stage 1 I took 319th out of 1,918 people, landing me in the top 17%. But publicly, which is only tested on, I want to say about 5% of the data, I was at 39th, and I was really comfortable and really excited for where I was landing, but I did get bumped down ultimately at the end because it tests it on all of the data. But still landing 158th out of 1,918 people is pretty significant, and I landed in the top 9%. So for the winter solutions and the future work of what I hope to be researching more of is the people that ended up getting the very first place had an IOU accuracy of 25.4%, which again doesn't seem that significant, but that's because of just how difficult it is to get a correct or accurate model. And the second place person had a difference of 1% at 24.3%. So that just goes to show how much variance there is within the scoring. But they use a 5-model ensemble, and there's also some more of the advanced techniques that they use listed there. But the majority of the people used MassStar CNN algorithms, but they were heavily simplified by using RetNet, and also smaller configuration numbers. And then one person used ChecksNet with a well-defined loss function, which is something that I hope to explore later. And they used heat mapping in DenseNet 1.1. And so for future work, these are some very technical details of what I hope to work with, but the bottom one is one of the most important, using better resources. So having more GPUs or more powerful GPUs and more computational power, as well as no timeout when I'm running my models. And so the way that this transfers over to the entire application of medical imaging is that I was just trying to indicate whether or not a patient had pneumonia and where specifically. But to predict any abnormality and give doctors and nurses more time to research other areas and further the medical field is very significant. And also, a Stanford study showed that for every 100 healthy patients, about 5 people were saved from unnecessarily being considered for surgery in an ACL study, but when they used model assistance. So this is running the images through the AI that people have been able to build, and it's a very significant increase that they were able to see in importance. So as for the why, Cassie, you can come on there. But for my half specifically, the biggest important factors of why I decided to research on this was I'm going to have a published research paper, which is really significant, but also I'm helping advance the computer science, information science, and medical fields, and then building my resume for graduate school and the rest of my career. But of course, I had a ton of fun doing this, and if any of you guys are interested, you should definitely talk to Dr. Chen and Dr. Bidden.
And I'm graduating in the spring, and I'm hoping to go into a career in data science. So for me, it was just more, just another opportunity to learn a lot, get more experience with working with models. This is my second semester doing the machine learning group. And the first time I focused on doing a model or building a model like Christian did. So this year I got to spend time doing a course on something called Coursera, which is where I learned everything. It was really interesting to focus this semester on the background behind everything. So when I go into a job interview or something, I'll know kind of what I'm talking about. Yeah, and it's fun. Everyone be here.
Definitely.
Yeah, learn some sources, I guess. More reputation.
Yeah, so definitely special thank you to Dr. Bidden and Dr. Chen for all of their work with us. But